Transformers are very useful. They're found in many applications. And the idea of a transformer is one coil we call the primary, and it has a number of turns around this laminated metal structure, and we have a secondary coil around the same laminated metal structure, and the primary usually has some kind of potential hooked across it, and this coil is going to produce a flux inside this metal laminated piece. So there's going to be some flux inside this metal, and so as the primary coil makes the flux, this metal is designed to focus or maintain all of that flux inside, and so that flux goes through the secondary of the transformer. So let's write the equations here for using Faraday's law. So the voltage potential in the secondary is equal to the negative number of turns in the secondary times the differential of the flux with respect to time. And I can just write this flux is equal to the potential divided by the number of turns. And let's do the same thing for the primary. Simplify it, put the derivative on the other side. And now, because these two derivatives are equal, we can say that negative Vs over Ns is equal to negative Vp over Np. I see a mistake I made here. Okay, and we can simplify this formula by doing cross products. Of course, the negatives will come out, and we can do cross products, move things around, and we will get that Vp over Vs is equal to Np over Ns. So the ratio of the voltages is determined by the number of turns in each of these coils. So the method to find the current relationship, well, we have to think about power. The power in the primary has to equal, if it's a lossless transformer, the power in the secondary. Transformer cannot create energy, it just transforms it from one coil to another. And so we have that Vp Ip is equal to Vs Is, and if I take and change my multiplication here into ratios, I have Vs over, Vp over Vs is equal to Is over Ip, So when I do the cross products, I still have the same thing, but VP over VS is NP over NS. So notice that the potential primary is correlated with the number of turns in the primary, but the current in the secondary is related to the number of turns in the primary. And the same for the denominators. The voltage of the secondary is related to the number of turns in the secondary, but the current in the primary is related to the number of turns in the secondary. So there are two possibilities for a transformer, actually three. There's a step up, and that's when VP is less than VS, and that means that NP is less than VS, in NS, but it also means that IP is greater than IS. So the current in the primary will be greater than the current in the secondary, but the potential in the primary will be less than the potential in the secondary. So these two relationships are different. They're opposite. Then you have a step down, and here VP is going to be greater than VS, NP is going to be greater than NS, and IP, current in the primary, is going to be less than IS, current in the secondary. Now, there is another form, it's used in specific applications, called an isolation transformer, and that means that VP is equal to VS, NP is equal to NS, and IP is equal to IS. These are used to do just what the name says, isolate. You completely separate two circuits from each other. You'll find that they're used in the medical field quite a bit, because by law you can't hook somebody directly to a piece of electrical machinery. If something were to happen, the isolation transformer would, in a sense, isolate the patient from the device. And these isolation transformers can be made so that they disconnect if something were to go wrong with the equipment. So transformers are very useful, and they're very easy to work with the relationships. So let's do an example.